This is our throttle handle. This is the L298N module. This is basically an H bridge. You can use other H bridge as well, and these are the motors, small motors. If you have bigger motor, just use a bigger H bridge. Rest will remain the same. This is our PIC16F877A. These two wires are the signal wires. See, now this is the handle. I move it. See, the speed increases. See, slow, very smooth. Speed increases. I rotate it further. It is further increasing the speed, like in a motorbike it happens. The more I rotate it, the speed increases more. See, I am rotating it, the speed is increasing with every bit of rotation. See, now this is at the maximum. Now I release it, the speed will decrease. See, the speed starts to decrease. The more I release it, the more speed decreases. See, it goes down. Now it's at maximum, I release it, 0. Half, release it, 0. See that, it's simple as that. Hello guys, welcome to learning microcontrollers. In this video, I'm gonna show you how you can interface an electric bike throttle handle to control the speed of a DC motor using an H bridge. That's what I'm gonna show you here. So these are the throttle handles easily available in the market nowadays. I will show you how you can connect it to a normal DC motor using an H bridge. I will use for the demonstration purpose, I will be using an L298 H bridge. You can use the other H bridges as well, they all do the same. So only to, if you have a bigger motor, you will need a bigger H bridge. Rest of your design circuit schematic will remain the same. The rest will remain the same. This handle will be able to run any type of motor if you have appropriate H bridge, and PIC will remain the same. This handle will remain the same. Only difference will be how much heavy motor you get. Thus, at the same value, you have to make a new H bridge. That's all. Rest will remain the same. So let me show you what I had bought this from the market. They are nowadays easily available in the market and very cheap. So you can see that it has 3 pins, green, black, red, and I don't know in your what will be the color code, but they all do the same. There might be, they replace usually sometime red with white, and they make the black like yellow, and the green mostly is ADC pin. It can be orange, it can be yellow, but whatever the color code will be, you can check the data sheet. They will have the same pin layout. Red is the power, then you have ground, and then you have the ADC pin. These three labeling will remain the same no matter whatever the color code is. You have to check the data sheet to get these pins. Okay, the red is power, black is ground, and green one is the ADC. Now before I continue, first we check it what it gives at the output. So whatever you get at this point, that is a voltage at ADC pin, you will put a DMM, one to the ADC pin, this pin. This is the ADC pin, green one, you will put a DMM one pin here, and then the other pin to the ground in the center. So you will put one DMM pin on the green and one on the ground, and then you will apply this formula. Whatever the voltage you get from there, you will put here. Max resolution of ADC, you will multiply this by max resolution of ADC, then the reference voltage divided by the reference voltage, this overall multiplication of both. So here the voltage at ADC pin is whatever you get by placing the DMM at ADC and ground pin of throttle handle. Then max resolution of ADC, we know that we are using PIC16F877A in this demonstration. So the ADC resolution as per the data sheet of PIC16F877A is 2 power 10, 10 bit ADC. This means that maximum it can have is 0 to 1023 or total of 1024 values. So it's 10 bit ADC, and whatever the microcontroller, if you use PIC32 etc., you might get to a 14 bit ADC. Then only this thing will change in the formula, rest will remain the same. Then guys, the final thing is the reference voltage. Reference voltage is the voltage you give to the ADC pin and also to the device. We will give 5 volt to both, to the PIC and to the device as well. So this will be the 5 volt. Now this formula becomes ADC value, voltage at the ADC pin, multiplied by 1024 and 5. They will remain constant, only this will change. So you just place a DMM, whatever the value you get, that is your ADC value. So two values are necessary to be taken, initial, and you will grade it to the maximum and the maximum value. That's why this is important. Now take a look here. This is our throttle handle, the type I got from the market. You may get the other one, better one, whatever you get, but they will have 3 pins like this, and these 3 pins will be common, power, ground, and ADC pin. Now guys, we are using PIC16F877A, ADC is 10 bit. At initial position, what I found is that ADC output is 176. How I got 176? Just apply this formula. Whatever the ADC value is, voltage at ADC pin, multiply by 1024 divided by 5, and you will get the ADC value. The ADC value that first I got is the 176, because these ADC values are read by the PIC. you will get them in the same form after the ADC conversion into the PIC microcontroller. So that's why we need these values. That's why we will do this math. So ADC output is 176 at maximum at initial position. When there is no rotation, just at the initial position, you are not touching it, it's 176 maximum. Then what I found out is that at maximum position it is 857. So we subtract the maximum from the minimum, we get 681 like this, and so maximum steps are 681. And then PIC16F877A PWM, because we will need to control the speed, and for that we will need the PWM of the PIC16F877A. It's 8-bit. A maximum 8-bit means it can supply a duty cycle of maximum 0 to 255 or 256. 2 power 8 is equal to 256. So we will need a value below 255 to make it work. So we divide the 681 by 255, we get 2.67. Now these are basic calculations. You will see when I will do the programming, they will be helpful. I'm just giving you a initial overview. So you can see that we got 2.67. Now whenever we will multiply any value within, like this is the initial, this is the maximum. So when you rotate it, rest of the values are in between this. Either it is above 176 or below 857. At center it will be in between these. Whatever you rotate at any point, the value is in between these two. This is maximum, this is the initial point. So we multiply that value with 2.67, or sorry, divide that value with the 2.67, and our value will always be below 255. It is like setting a ratio that the value must be below 255, because maximum duty cycle that we can give is 255 to the PICs from the PICs PWM pin to the L298N driver. Now guys, this is the L298N and this is the car I am going to use for demonstration purpose. I will only use one gate, not both gates, and I will show you how to connect it and run it, control the speed using this throttle handle. So you can see that L298N has a very clear labeling on its body as well. Still I label them for you. You can see it is the pin labeled as 12 volt. You can maximum go 36 volt, and behind it here is a jumper. If you connect this jumper, this pin and the third pin gets connected. This pin over here is a 5 volt pin, and there is a on board 7805 voltage regulator. So this voltage regulator will enable you to use the 5 volt directly converted from this 12 volt. You don't have to connect it separately. So this will be shown in the next slide. So right now you connect your main battery here, then you connect the ground here, and then you have this 5 volt here. If you have connected this jumper over here, then there is a voltage in the 5 volt. So this 5 volt will enable the this whole circuit here for the giving the logics. I will show you in the next slide. So here you have your motors. See, this motor has two terminals, red and black, red and black. You connect them in cross like this. You connect them in cross and send them to the output 3. It has two gates. This is output 1, output 2. I am using the lower gate, output 3 and output 4. You can use both gates as well to increase the current, but right now I am only going to use this gate. So for the black, just connect them in cross like this and send it to the output 4 like this. Now this will allow us to send logics to the PIC from the PIC. Now let's see how to connect it to the PIC. You have to do these power connections before coming to this logic connection. Now let's do the logic connection. This is our throttle handle and this is our L298N module. Let's connect the throttle handle first. As you know, I had shown you in the previous slide, it has 3 pins, ADC, ground and power pin like this. So you connect the ADC pin directly to any available ADC pin of the PIC like this. Then ground will go to the ground of PIC, power will go to the power of PIC. So we gave 5 volt to the throttle handle through PIC. Now guys, for the L298N module, that is basically the H bridge. You can use any other H bridge as well. All H bridge have these things in common. Even if you make your own, H bridge has these things in common. So for the motor, I am going to use a TT motor. For that, this bridge can provide up to 2.5 ampere of current. That is more than enough. So this is the battery over here. I am going to use 0 to 15 volt maximum for this type of motor. So battery always has two terminals, one positive, one negative. Then I label it like this leftmost pin on this terminal is 0 to 15 volt for this motor. Then the center one is the ground. Then we have 5 volt pin. Now this jumper you can see over here is connected to this 7805 regulator. If you connect this jumper, then 5 volt is already there. You don't have to separately like give 5 volt for the IC. This 5 volt will run the IC and IC will run this whole circuit over here. Now guys, this we are only going to use this second gate, output 3 and 4. So we don't need to enable this gate 1. So you can remove this ENA1 jumper. For the ENA2, you have to connect a jumper here. This, or either you will give 5 volt from here to here or from your PIC to here, depending upon whatever you prefer. But if you simply put a jumper here, then this 5 volt and these both jumper, this jumper and this jumper, 5 volt will automatically come to this pin through this 7805 regulator. This is like I am giving like 7 to 8 volt, this will be converted to 5 volt. So enable B, the second gate is now enabled. IN3 and IN4 are for the second gate for the output 3 and output 4. Now IN4 and IN3 are enabled, we can connect them to the PIC. First of all, you connect the center ground with the ground of the PIC like this. Then the same ground will also go to the battery like this. You have to connect it to the battery, whatever the power source you are going to use, or a DC power supply, whatever it is. Then guys, you connect your 0 to 15 volt to the battery, that is the source for the motor. This will go to the motor, do not connect it to the PIC, only to this L298 and driver. Then guys, you connect your logics. IN3, I am going to send it to the CCP PWM 1 pin. On the data sheet, it is labeled as CCP 1 pin, pin number 17 of the PIC. And IN4, I will send it to the PWM 2 pin, that is CCP 2 on that data sheet. In this way, our pins are connected to the PWM pin because PWM will allow us to change the speed of the DC motor. Now, this is overall connection. So, let me introduce you to the hardware before we move on to the programming. So guys, this is our hardware over here. As you can see, this is the lever, this is our motors. Only these two motors will work. I am only using this gate over here, and this is the battery you can see, and over there is our PIC16F877A, and the wiring are as shown in the presentation. And how to set up this hardware, I will share the link of the video in the description. So you can see how you can set up your own hardware as well. This is not difficult. It is just a trainer. That's why it looks like it's very big. It's basically just a small circuit. You only have to connect the PIC. Rest of it, guys, you can see that handle PIC 3.5, PIC16F877A, and our motor and L298 and H bridge module. So when you will use a bigger motor, you will simply replace this L298 and module with a bigger H bridge, or you can make your own H bridge as well. Handle will remain the same, PIC will remain the same, these connections will remain the same. Only the difference will be that your voltage source will be bigger, your L298 and IC will be bigger, and your motors will be bigger. Rest will remain the same. It's simple as that. So let's get to the MicroC for PIC programming. This is our MicroC for PIC. Let me zoom in so you guys can see better. So as you can see, it's version 7.2.0. You can use a higher version as well. Higher is always better. Now click on File, New Project. This window pops up, New Project Wizard. Click on Next, write the name of the project. I write Throttle Handle Based Speed Control DC Motor using H bridge tutorial by learning microcontrollers. So this is a name I wrote. You can write whatever the name you want. So this is the path where this will be stored, and this is PIC16F877A microcontroller I'm going to use here. Select the one you are going to use. I'm going to use a PIC16F877A, and the device clock is the crystal connected to pin number 13 and 14 of your PIC. I have a 20 MHz crystal connected there, so that's why I'm going to use a 20. So click on Next and Finish. Okay, this window pops up. Before you do anything else, first of all, press Ctrl S to save your work like this. Now go to the right in the libraries, expand this MicroC library, expand the system libraries. Here select the libraries you are going to use. We are going to need the ADC library for the throttle handle. Then we are going to need the PWM library for generating the output commands to control the speed of a DC motor using H bridge. Simple as that. First of all, we initialize the ADC pins. So click on it. This is our ADC I90 command. Now go back, place it below the void main. This command will initialize all the ADC pin of your PIC. We are only going to need one, but we are going to initialize all the pins because we are not going to do anything else with the rest of the pins, at least in my case. So I will initialize this and will give some initialization delay. This initialization delay is not necessary in the newer versions of MicroC for PIC. In the older versions, there used to be some bypassing of commands, but in the newer version it has no use, but I suggest you still give it in the one-time loop. So ADC pins are initialized. Now we initialize the PWM pins. So we have connected both the PWM 1 pins, one for the forward direction, one for the reverse direction. But in our case, I will simply demonstrate this to you using programming. So I initialize the PWM 1, double click on this PWM 1 I90 command, this command, paste it below this like this. This over here is the frequency. It's initialized at 5000 frequency for the L298, and this is enough. You have to look at the data sheet of the H bridge you are going to use, the transistors you are going to use, or MOSFET, whatever. you have to look there what is the minimum and maximum requirement of frequency to control that H bridge. Then you will set the frequency here. In case of L298 and 5 kHz is fine. So PWM1 is initialized. I give some initialization delay. Now let's initialize the PWM2. That is pin number 16. So paste it. Just replace this 1 with 2. This will initialize the PWM2 as well. Now guys, the next thing is we have our PWMs initialized. Now we go to our forever loop. Write down while 1. Forever loop starts here and here. And in between this, you will write your code. First of all, we will need to read the value from the sensor. Above the void main, write, take an integer ADC val. That is what I give it the name. So paste it here and write down the command. Write down the command ADC underscore read from which channel? Channel 0. So this command over here is the syntax for the ADC read command. This command will read the data from the sensor after converting it to ADC. So this variable is variable in which the converted value analog to digital converted value, the digital value will be stored in the form of integers. You can use floats as well, but integer is fine. I'm not going to go for much accuracy. Its accuracy is good enough. So and this over here is the channels. 0 means it will receive data from the channel AN0, that is pin number 2 of the PIC. If your sensor is connected to the pin number 3, that is AN1 on the data sheet, then you will write 1 here. If it is connected to AN2, then you will write 2 here. Whatever the channel you are using, simply write the name of that pin. Now give some initialization delay. Not necessary, but I suggest you give it like this. Now we have our ADC value in our hand. Now we will perform the calculations which I had shown you before in the presentation here. That's why I showed you those calculations. So this is the value. It is right now, I told you initially the value we are getting is 176. I show you in the presentation. Over here you can see that I found out that the initial value is 176. You can find it out by connecting a DMM as well. So if the initially it is at 176, so we can subtract like whatever the value is initially minus 176. So we don't need that value. Rest of the values are doing nothing. So I delete this value. Now the next thing we did was that we took the ADC and now maximum PWM output that we can generate is 8-bit, that is maximum of 0 to 255 duty cycle. So we have to bring this value and the maximum value in between that limit. For that we did another calculation over there. So I show you that. See that over here we have these calculations. See, it says the maximum value was 857, the minimum is 176. So 681 is a useful ADC value that will affect the speed. So, but we have maximum PWM duty cycles that we can provide to the H bridge is 255, 0 to 255. So we divide this by this. So whenever whatever the value that comes in between 176 and 857 will be like will be maximum 681 because we had subtracted minus 176 from the original value. So that value will be divided by 2.67 and it will come within the range of 255. It will be 254, 253, whatever the value it will become. So it will work in proportion. So that's why we will divide it by 2.67 to bring it in the range. So what we do is that we write this over here, now divided by 2.67 like this. Now we have our whatever this value is, now it is in the range of 255, which is acceptable to our duty cycle command. Now what I do is that I start the PWM, go to PWM1 start. Only one direction, PWM1 will be for the one direction and PWM2 will be for the other direction. Only PWM1 start, and then I write here PWM1 set duty cycle. This is the other command, this one. Double click on it. This will lead you to this page over here. Here you have this command. Now see here it also says here that PWM sets PWM duty ratio from 0 to 255. This means 8-bit. So that was the problem. That's why we did the calculations to bring the value within the limit of 255. I place it here, and now what is this value will be our duty cycle like this. Now I give some delay. 25 will do fine. In the newer versions of MicroC, you have to be careful with capital and smaller letters. Even this can give an error. So 25 will do fine. That's just for safety. Okay, this is enough. So what is happening here is that we are reading value from the sensor, we are calibrating the value to bring in the 2 power 8, that is 8-bit PWM duty cycle limit, and then we start the PWM one, and then we will whatever the value is coming from the throttle handle, that will be given to the PWM and it will give it to the H bridge, and H will drive the motor accordingly. So we build this code and see what happens. So successfully built, no errors. Go to the PIC16 programmer tool over here. You select your microcontroller. I have PIC16F877A. Click the file, import hex file, throttle handle base speed control. This was the one we just created. I click on write. Okay, the new file is being written. Let's get to the hardware. Okay, this is our hardware over here. Let's see what happens. Okay, it's on and it's a good sign. By default, it's not working. Now I pick up the handle and I rotate it. See, the motor moves, and I rotate it more, it goes higher speed. Further rotation goes higher speed. Now it is at the highest speed, at the maximum rotation. See that? Now I slow down. It is slowing down. See, it is very slow and it is very smooth. It is a very good handle, I will say, at this cost. See, I leave it. Now it's below 176. Doing nothing. Now again. See, it is moving. See, further speed is increasing. More speed, more. Now this is the maximum speed. Now again I lower down the speed. See, very smooth. It is very smooth, and leave it. So that's how it's gonna work. Now we go for the opposite direction with the other pin, CCP2 pin. Just go back. So what we do here is that I comment this. So we also have this when I will give you the code in the description. So copy this over here. Now instead of 1, just make these ones 2. PWM2 start, PWM2 set duty cycle, that's all. Now this will be the opposite direction because our PWM2 pin is connected to IN4. IN4 of the L29A10, that is the H bridge second input. So I write this code. Everything will be same, only direction will be reversed. So let's see what happens this time. So we power it up using, okay, we are using 2, okay, it's powered up already. So that's good. See, this is a good sign. It is not moving. Also the circuit is powered up. Now I move the handle. See, direction has reversed. Rest is same. See. So this is, I think, the minimum speed we can go. It's very smooth. I think its resolution is infinite. The smoother you can pull it, the smoother it goes. Then it starts to increase, goes further up, and this is the maximum. I release it, it goes down, 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 down. So guys, this is simple as that. If you have any questions, you can ask in the description of, in the comment section of the video. I will share the code in the description, and I hope you guys learned something from this video. Thank you very much for your time and interest and patience. We'll see you in the next video. Goodbye.